All right, we're at a new pattern, the eighth pattern. For the problems that we're solving, top key elements, introduction. Here's an overview. And essentially what it's trying to say is get the top k, where k is an arbitrary number of elements, from a given amount of data most optimally. And the key to this is to use a heap, whether a minimum or a maximum heap. And they give this nice example, I would say. It's a super nice example where we're supposed to get the top 3 largest elements from an unsorted array. So the array is not sorted, right? Otherwise, we just slice maybe the end of it and return. But it's not sorted. So what do? You maintain a minimum heap of the first k elements. You put k elements into that heap. Then you have a pointer that moves through the rest of the array and checks if you see something bigger, pop the root of the minimum heap and replace and push that value into the heap. So in this case, 3 is smaller than 4, so it cannot be the top in the top 3 like list of elements in the whole array. So we push 4 into the heap and pop 3 off of it, like so. Next, we evaluate 2. 2 is smaller than 4, so it can't be top k elements, in this case top 3 elements, so we don't do anything. 12 is bigger than 4. That means 4 doesn't belong here, so we pop 4 off and push 12 on there. So 5 is therefore the third smallest element in this whole array right now. Not the third smallest element, supposedly the third largest element, because we're looking for the top 3 elements in magnitude from this unsorted set of data. Next, we're considering 15, and 15 is bigger than 5, so 5 of it doesn't belong in the top 3 then. So we remove it and replace it with 15, and we're at the end of the list, so we know that we have the top 3 largest elements in this unsorted array right here. It's pretty cool. And it usually gives us n log n time to do things. So that is the overview of this problem. And so n log k in this case, because you don't have to sort the list first, because sorting takes n log n best case, right? And finding will take O of k time after you sorted it. So it's this plus this, but in this case you just get this, right? Log of k, because that's heap insertion performance, and you have to loop through the entire list at least once, so that's where the n comes from. So yeah, we can look at some examples. So sorting the characters by frequency. So first of all, you put the character counts in a hash map, and you can use a heap to keep track of the most frequent or least frequent character, depending on what you want. I didn't really understand why this example, so I'm not going to cover it, but I mean, you can read it if you want. So, does my problem match this pattern? Yes, if these are fulfilled. If you want the largest, smallest, most frequent, or least frequent subset of elements in an unsorted list, this is key. The list isn't sorted. Because if it was sorted, you don't need a heap, right? You just pull it out of there. Could be part of the final solution or an intermediate step towards the final solution. You don't need it if it doesn't support random access. So if it's not an array, you don't need it if, for example, if it's not an array. You don't need it if it's already sorted according to the relevant criteria, right? Because you could just pull it out of there. And if only one extreme value. So if you're looking for only the largest value, you can do that in O of n, which is better than O of n log k, with a simple scan through the input array. So now real world problems. You can use it for Uber, so the n nearest drivers within a user's vicinity. Avoiding drivers that are too far away, so you don't have to sort. Because I think when you do like an SQL query and you sort, it's sorting the whole list already, so it's not as efficient as just stepping through every single thing using this heap pattern. And at uber scale, I guess that importance, that difference in time complexity would be worth quite a few millions of USD in server costs. Next, given the set of IDs, another example where this pattern is useful is with stocks. So you have IDs of brokers, determine the top K brokers' performance with the frequently repeated IDs in the given data set. So similar to the this example with sort characters by frequency, it seems. Yeah, so last we have this strategy question. So problems that can be solved through the key elements pattern. Rearrange the given string so that no two identical characters are adjacent to each other. And I think I got this wrong actually here. Yeah, I thought it was some other pattern, but it turns out to be a top key elements pattern. And the explanation is here. So we wanted to rearrange a string so that no two identical characters are adjacent to each other. So most frequent occurring characters first, then next most frequent element, and so on. I don't really understand that. I know this is not doesn't belong to the pattern. I can probably understand this if I rest or just take my time to read it, but it's fine if I don't right now. I'm sure I'll find a problem that will make it clearer. 5 nearest points to origin. It sounds about right. About that, right? Implement a stack in which the population was the most frequent element. I said it was this, but I was wrong for some reason. Here's the reason. So I don't know why that didn't work either, but it didn't apparently. And so this belonged here, while this didn't belong there. I'll be alright though. That's all with the introduction. See you in the next video. Cheers.